Good morning, everybody. Myself, Appana Jaratnothu. Today, let's see the Nando Tetris Project 2. In the Nando Tetris Project 1, we have seen the building of basic chips or basic gates like AND gate, OR gate, XOR gate, and basic chips like AND 16 chips, not 16 chips, NAND 16 chips, or the more complex gates like XOR, XOR 16s and MUX demugs. So in this way, we have completed the project one with basic structure of gates. The next step is the computer system. First, let's see the one human architecture. Here, it, if we give the input, it will be accessed through the memory, and CPU, ALU, and registers, which is a central unit, will be useful for doing the operations, and it will give the output. Uh, in this project, we'll see regarding arithmetic logical unit. It is the centerpiece of the computer's architecture, and it is the computational centerpiece of the CPU is the ALU. Here, the different arithmetic and logical functions can be executed. For a general ALU, two inputs are given x and y. A function is applied on the inputs and we get an output. In this diagram, we can observe that input 1 and input 2 are given and a function is applied on both these numbers, and we get output which is made up of input 1 and 2. So ALU can be functioned in different ways. Functions of ALU can be of different types. Arithmetic functions, which are addition, subtraction, multiplication, division, and etc. Logical functions can be AND, OR, XOR, etc. So as we are making a hack computer, it will be the hack ALU. So this is the diagram or pictorial representation of an ALU. The hack ALU, it operates on two 16-bit 2's complement values. Those are the inputs x and y. Outputs a 16-bit 2's complement value. Also outputs two 1-bit value. Those are ZR and NG. These are the control bits, and which functions can be executed is set of 6 one input bits. ZX, NX, ZY, NY, F and NO can be combined in different ways to perform a particular operation. We have two other control bits which are ZR and NG, which are discussed earlier. If the output becomes 0, ZR will become 1, or else it will be 0, and if the output will be negative, then the NG becomes 1, otherwise 0. So as discussed earlier, we have these functions, right? 6 functions. This can be classified into 6 different ways and computed differently. So these control bits and functions. If ZX will be NX, ZY, NY, F and NO, the output will be these different parts. So if the ZX will be 1, if NX will be 0, if ZY will be 1 and NY will be 0, and if F is 1 and NO is 0, we get zeros. So in this way, we can execute, we can bring it 0, we can bring it 1, we get -1, the direct X can be brought out, the direct Y can be brought out, the negation of X, the negation of Y, or the minus of X on minus of Y, and x plus 1 increment of 1, y plus 1 increment of y, x minus 1 subtraction by 1, y minus 1 subtraction of y, x plus y addition of both x and y, and x minus y, which is the subtraction of x and y minus x the complement of the earlier one, which is y minus x, and x and y the AND operation, x or y the OR operation. So we'll get these resulting ALU outputs. So in the project 2, we create the hack ALU, and we need the other chips before the old chips which are made. Those can be made. Those are half adder, full adder, 16-bit addition of gates, or 16-bit increment gates, and ALU. These chips should be written in hardware description language. It is also called as HDL. So half adder, the HDL code of half adder is uh, if we give two inputs A and B, output will be sum and carry. So in this diagram, we can observe if we give A and B, it gives sum and carries. So if the the input is 0 and 0, sum of both of them will be 0, and both carry will also be 0. As it is a binary value, it can occupy only 0 and 1s. So if we add 0 and 1, we get 1. And if we there is no carry here, so the carry will be 0. And again, in the case of 1 and 0, the output will be same. The sum will be 1 and carry will be 0. And if you add 1 and 1, we get 2. But as it is a representation on binary, the sum of both of them will be 0 and carry will be 1. And if we observe, the sum can be in the form of AND gate, so sum will be the form of XOR gate, and carry will be form of AND gate. So that's the reason we used built-in gates AND and XOR to make an half adder. So this is the first gate which we are going to build, first chip which we are going to build. The second chip is full adder. So in this chip, it is a modification of half adder. Uh, Here the input can be ABC, output is sum and carry. So if the half adder inputs A, B and sum 1 and carry is C1, and half adder inputs as S1, because the AB sum can be given to C and they both sum and carry can be given out. And in this way we can get R of A and C1 and B of C2, which is given to out of carry. So in this way, if we have A, B and C three different values, we get two values of sum and carry. This is the implementation of full adder. So if it is asked about A and B addition side by side, here we can see in the chip 16-bit addition, the first part we have only 1 and 0. So we can use only half adder at first, and rest all we can have three different units to be added. So first we can use a half adder, and then rest we can be added as full adders. So the outputs of first or second can be used as the third one. The carries of first can be used as the second input. So in the same way, first one half adder will be executed and rest all can be the full adders. This is the implementation of add 16 chip. And then if you have increment 16, first we give only the true value, the basic one will be 1, and we should just increment all the values with 1. So in this way we can get one value incremented with the given value. And finally the ALU. All the chips which we have made till now can be used in ALU, and according to all the implementation according to this table, what are the implementation we can execute, and we can get the resulting ALU. And if you see in the hardware simulator, so this is how hardware simulator looks. We can load the chips through this value, and here we can execute or evaluate the chip logic, and we can inspect the ALU outputs here. Here we can set the ALU inputs and control bits to test some values. And if you take the built-in ALU, then we can get some GUI side effects, and built-in ALU implementation will be seen in this HTL block. So let's go into the hardware simulator and test it. So according to us, the ALU HTL can be written with the basic gates in this way. So as they gave the implementation as set x is 0 and set is equal to 1 and so on, in this way we can take all this as input values, and output we have output 16-bit output, one ZR control bit and one NG control bit. So if we need 0 implementation, we can choose mux, and if we need a negation implementation, we can use not and mux. And if you need to choose between add 16 and AND 16, you can use mux 16, add 16 and mux 16 again. So if you need negation, we can use the not 16 gate which we built in first project. And to indicate if the numbers is negative or 0 by the methods of 2 complement, we can use mux or and not, and we can give out the ZR and NG values. Yes. So if we go to the tools and select the hardware simulation, yeah, the hardware simulation is open. So if we choose our bits from the projects, or from the project 2, if we select some full adder chip, okay, we are loading the full adder chip. So here we can see the HTL code of the full adder, the same which was in the PPT, and these are the internal pins, this is the output pins, and this is the input pins. So we can give different values here, 1, 0 and 1. Okay, let it change into binary values. Okay, so after giving the input values, if we evaluate, we get sum as 0 and carry as 1. As we know, 1 plus 0 plus 1 is 2. And as it is a binary, we can 2 is represented as 1 0. So carry will be going to 1 and sum is to 0. So if we test through test gate, so here the full adder, if we load the script and we evaluate, it is evaluated serially and we get the output in the output screen, or we can compare it through the compare screen. So yes, here all the values are executed. That means the written code is correct. And after doing the loading chip which we wrote, now we can load the built-in chips to test the ALU and get the feeling of GUI. In tools we have built-in chips. Here we can select the ALU chip, and when we select the ALU chip, here we get a GUI representation. So if we go back again and take that testing page, um, yeah, in projects, second project we have then ALU testing. So if you load the script, you can choose this, and yeah, after executing, you can get the same compare. You can get the same compare values. You can compare accordingly. The increase in speed will increase the execution time. Yes. So after increasing the speed, the execution is very fast. And now if you go back and see the program flow with given values. Okay, let's give the one as input. And here if you change the input value again, and if you want to the ALU thing, uh, evaluating it, we can get the GUI representation. Let's load the chip again. After loading the built-in chip, inserting these values, if you take 1 1 1 here, and if you take 1 1 1 here, and evaluating it, the D input and MA input can be shown here, and ALU output can be shown here. So, and as all are zeros, we can get just 0 as output. According to the table, we can give values to these inputs and evaluate the answers. According to that table, if we want negation of x, we can take 0 0 1. So if you take 0 0 1 1 1 1, so after putting 0 0 1 1 1 1 and evaluating it, we get the minus 7. The minus x will get the minus x. The input is 7 and we get the minus 7. And if you want this in a binary, okay, here only the decimal representation will be shown. So your 7 will get the minus 7. In this way, we can get the ALU representation also. Here, the built-in ALU can be executed. In the similar way, we can execute all the other functions. In this way, we conclude this lecture, the project 2. Thank you.